When we write a number in decimal notation, we're expressing a number by expressing how many copies of each power of 10 are in the number. For example, 375 is the number that's equal to 3 copies of 10 squared plus 7 copies of 10 to the first plus 5 copies of 10 to the 0. This extends to negative powers of 10 also, which enables us to express numbers that aren't whole. For example, 375.2 is 3 times 10 squared plus 7 times 10 to the first plus 5 times 10 to the 0 plus 2 times 10 to the negative 1. Another example is 1/7, which equals 0.142857142857. That pattern continues with the initial string of 6 digits repeating without end. We can write 1/7 like this, as a sum of copies of negative powers of 10 that never ends. But how do we make sense of those 3 dots at the end? What does it mean to add infinitely many numbers together? This motivates the next definition. An infinite series, or simply a series, is an expression of this form for some sequence of numbers a sub n. We also use this notation to denote a series. The implication is, of course, that a series is a sum, but for now it's really just a formal expression. Let's make 2 remarks. First, when determining whether or not something is a series, it doesn't matter where we start our indexing, so this thing is also a series. Second, the letter used for indexing doesn't matter either, as long as we don't use a letter that's already being used for something. For example, the sum from n equals 0 to infinity of a sub n is the same as the sum from I equals 0 to infinity of a sub I. They both equal a sub 0 plus a sub 1 plus a sub 2, and so on. Let's look at 2 examples of series. First, this series is the harmonic series. This is an important example that will appear many times as we learn more about series. Second, this is an example of a geometric series, which we'll define later, not in this video. We've defined a series as an expression with a particular form, just as a decimal expansion of a number is a particular expression of that number, not the number itself. But when does a series represent a number? To answer this, we use sequences. Let's return to our example with 1/3. If we want to approximate 1/3 with a terminating decimal expansion, then we can apply the long division algorithm to produce a number such as 0.3333 with a remainder of 3 over 100,000. This means that 1/3 is almost equal to 0.3333, which we can express as this finite sum. As n grows without bound, this sum becomes an ever better approximation of 1/3. To put this in terms of sequences, let's define s sub n to be the sum from I equals 1 to n of 3 times 10 to the negative I. Then the limit as n goes to infinity of s sub n equals 1/3. This leads to our next definition. The nth partial sum of a series, usually denoted by s sub n, is the sum of the first n terms of the series. For example, the 4th partial sum of this series is 3 over 10 plus 3 over 100 plus 3 over 1000 plus 3 over 10,000. We're now in a position to define what it means for a series to exist, not just as something we can write, but as something that has a numeric value. A convergent series is a series whose sequence of partial sums converges. The value of this limit is the value of the series. All other series are divergent. For example, the partial sums of the sum from n equals 1 to infinity of 3 times 10 to the negative n are all of the form 0.3333 and so on for some finite number of 3's, and the sequence of these converges to 1/3. As another example, the partial sums of the series 1, minus 1, plus 1, minus 1, plus 1, minus 1, and so on are 1, 0, 1, 0, and so on. This sequence doesn't converge. The series is therefore divergent. A final remark. Just as with any other limits, there are 2 special ways in which series can fail to exist. namely by approaching plus or minus infinity. For example, let's consider the series whose terms are the positive integers in ascending order. Then the limit of the partial sums is the limit of this expression, which diverges to infinity. So this series equals infinity. Strictly speaking, it diverges.